All right, good morning, everyone. So, today we'll start the last chapter, and that's going to be on your test in 2 days. Hopefully everyone remembers that test in 2 days. So basically, whatever we cover today and like half of tomorrow will show up from the potential section, which basically means that there won't be too much potential stuff on the exam. So it'll show up as like a part C somewhere, or maybe a short answer or things like that. But we still have to talk about it. So anyways, what this chapter wants us to do, wants us to start looking at, is the, first of all, relationship, or at least the comparison between gravitational force, Newton's universal law of gravity, and the electric force, i.e. Coulomb's law. So basically, what it wants us to see here is that what? Even though Fg, magnitude, is equal to Gm1, m2 divided by r squared, and Fe is equal to K, Q1, Q2 divided by r squared, they have exactly the same structure. So it's a constant, this is a constant, this is also a constant, divided by simply the separation distance between the two, squared. Now this one is always attractive, this one is sometimes repulsive, sometimes attractive, depending on how these charges align with each other, but they have the same structure, right? They're both proportional to whatever the distance squared. They're both inverse square laws. So why is that important? Well, if we go back to what we did in 205, remember that gravity is a conservative force. So, since Coulomb's law has exactly the same structure as the gravitational law, what that means is if this one is a conservative force, then this one should be a conservative force as well. So by simply looking at the structure, since the first one is conservative, well then this one should be conservative too. Why is that important? What is so special about conservative forces? What does a conservative force tell us? Everybody remember why conservative forces were special? What was unique about them? Why were they important? I'll give you a hint. Think about work. So conservative forces had everything to do with work. So what was important about work with the conservative force? Remember? Let's think about this. So if I had an object that I say brought from one point, let's call that point A, around say a closed loop, and I brought it back to point A, how much work did I do for a conservative force? How much work did I do to go through a closed loop for a conservative force? What do you think? Good, Nathaniel. 0. What was important about a conservative force was that the amount of work that I did bringing this thing through some closed loop was equal to 0, which implied to us the fact that if I brought it instead from point A to point B, it didn't matter how I went from point A to point B, whether I went this way, or if I went this way, or if I went this way, the works were identically the same, which meant that for conservative forces, the work is path independent. But what else is important about that? If my work is path independent, that means it doesn't matter the path at which I followed to get from point A to point B. All that matters is I went from point A to point B. From that, what could we define? So the ultimate reason that we care about conservative forces is because we could define something from it. I'll give you another hint. What units does work have? Say something. What units does work have? I'll give you a hint. It's capital J. Joules, fantastic. Joules are the units of energy, right? Which means that from work we can get energy, more specifically, what type of energy? Kinetic energy? No, potential energy. So the most important thing about conservative forces is that conservative forces, as long as the path is independent for work, means we can then derive from this or define a potential energy. So the fact that the electric force has exactly the same structure as the gravitational force, and the gravitational force was a conservative force, that then means that the electric force is also a conservative force, which means that the work then is path independent, which means we can define a potential energy, which means we have a now new type of energy we can talk about. Before we had gravitational potential energy, we had spring potential energy, now we're going to have an electric potential energy. So now we want to know, well, what does the electric potential energy look like? So how do we define electric potential energy? Now this is going to depend, and we'll talk about that, but remember that work is related to potential energy by the minus the change of potential energy. So this means if we determine the work which is happening then on an object, we can then determine its potential energy. So how would we do that? So, show you a video. So hopefully you can see this. I made this yesterday. It didn't turn out that great. It's much more impressive when you have it in front of you. But anyways, what's going on here is this is what's known as cathode ray tube. This is your old TVs. That's what this is. So basically your old two TVs, they're cathode ray tubes. So basically what's inside of here is a gas. You're then going to supply a huge electric field across this, which is then going to ionize the gas. Once the ionized gas, which means you're going to strip off electrons from the ionized gas, then they're going to accelerate from one side to the other side, which then manifests itself as a collimated beam. So what you should see across here, hopefully you can see it rather well, is you should see a beam going across here. And then what I'll do from there is I'll actually use a magnet, and I'll use the magnet behind it to actually deflect the beam in different directions to actually show to you it is charged particles, not just light. Okay? So hopefully this is what you're going to see. I'm going to use this to motivate the energy. So hopefully you can kind of see that beam. So the beam is actually running straight through here. And you can kind of see the beam if you look squint closely enough. So you can see part of it over here. So as I'm moving the magnet, you can see actually the beam moving up and down. Fortunately, the glare from my computer didn't come out that well. I tried it with the lights off and all kinds of different scenarios, but it always looked like crap. So you can kind of see it on the side there, so, but hopefully. Anyways, so this is the cathode ray tube, okay? So we're gonna use this idea to motivate our energy, okay? So let's talk about the energy then. So what's happening here is I have effectively two parallel plate capacitors. So let's say I have positive on this side. So these are positive charges. On this side, I then have negative charges. So let's put some negative charges in here. So that inside of here, I'm going to create an electric field, which then points from the positive to the negative. And we also know that this guy is equal to a constant because they're parallel plate capacitors. So good. So let's pretend for now that I don't know it's actually negative charges which are being pulled off, ionized, that they're actually positive charges. Let's just pretend. So let's say that I start off with a positive charge here, which has a charge of Q. And then this thing is going to feel a force then in what? This direction due to the electric field. So the force will be in the same direction as the electric field, which means it's going to be accelerated. So it's going to feel an acceleration in this direction. And let's say that these two plates are separated by a distance of d. So what happened? So let's pretend that initially this charged particle starts off with 0 velocity. So it's then going to feel an acceleration. It's going to increase velocity as it moves all the way across and then get moved to the other side. So what happens here then is that the electric field via the electric force is going to do work on the charged particle to move it from this plate here to this plate over here over the distance of d. So let's recall that work is equal to, in the case of a constant force, force dotted by the distance at which it moves, which is then equal to the force magnitude times the magnitude of the distance times cosine of the angle between the two. Now here, the force is actually the electric force. So this is just going to be equal to the electric force the distance it's going to move is the total distance across the plates, which is then FD, or just D in this case, times cosine area between the two, but in this case, what? The displacement is this way. So if I drew a displacement vector, that displacement vector then would point in this direction. So my displacement vector is this way, my force is this way, so what's the angle between the two? Guys are so lively today. Thank you. 0. What's cosine of 0? 1, right? So this says then that the work done by the electric field in the constant electric field to move it from this plate to this plate is simply the electric force times the distance. Well, we also know the electric force is simply equal to the charge of the charged particle times the electric field times the distance. Now, what we also know is by definition, this is equal to minus the change of potential energy. Now, let's call the left-hand side here A, and let's call the right-hand side B. So minus the change means what? So let's put the negative on the other side. So it's going to be equal to the change of potential energy is equal to negative the charge times the electric field times D. So this is equal to the final potential, which is the potential energy at B, minus the potential energy at A, is equal then to minus QE times D. Okay with this? Remember, delta is always final minus the initial. So this means the potential energy here at B minus then the potential energy at A is then equal to negative QD. What does this tell me? So first of all, to make sure that this thing is negative here, what does it tell me about the size of this guy relative to the size of this guy? What does that tell me? So if the right-hand side is negative, what has to be true about the size of the potential energy at A versus the potential energy at B? What has to be true? It's bigger, right? So what this tells me is that what? This thing started off in a region of high potential energy, gets accelerated then to a region of low potential energy. Have we seen that before? Yes, right? The reason that this thing falls down is because up here I have a high potential energy, here I have a low potential energy, so this thing falls because it seeks a place of low potential energy. That's exactly what's happening here. So the first thing we learn from here is that what? This is our high potential energy region. And this side over here is our low potential energy. So this thing wants to find a region of high potential energy to low potential energy. What this also tells me is if I call this region 0 potential energy, like we could with gravitational, right? I can always call the top of this stage my 0 potential energy region. This thing starts off with potential energy, ends with 0 potential energy. Eventually it's going to break. Which means that as long as I have a constant electric field, the potential energy then is simply equal to QED. That's my potential energy. So the other thing we learned from here is, as long as E is equal to a constant, then the potential energy then is equal to the charge times the electric field times the distance, which is the same thing as the electric force times the distance. This is my potential energy. Let's call this the electric potential energy. So ultimately, this thing does exactly what a particle falling in a gravitational field does. It seeks a region of high potential energy to a low potential energy, causing it to speed up. The other thing we know is that what? Here, the velocity here is going to be much, much smaller than the velocity on this side. So if this thing starts off with 0 velocity, here it's moving with non-zero velocity. So on this side, this is low velocity. And on this side, this is high velocity. Now, quick question. What would happen with an electron? So if this was a negative charge instead of a positive charge, what would it do instead? So which direction would it actually move? It'd move the opposite direction, right? So it had a negative charge would actually start here, accelerate in this direction, opposite the direction of the electric field, which means that an electron actually goes from low potential to high potential, opposite of what a positive charge does, which goes from high potential to low potential. A little bit backwards, but it's okay, because it's a negative charge. So that's actually what happens in a battery. What happens actually in a battery is instead of a charged particle being brought from the positive terminal to the negative terminal, it's actually brought from the negative to the positive. So it actually goes in the opposite direction. But anywho, so this is potential energy. Now again, this is only true for constant electric fields. We'll define it for non-constant electric fields. But for now, what this says is that we can define a potential energy because this thing is actually a conservative force. Now, for our purposes, it's much more convenient to define something else, which is what's known as the electric potential. So let's talk about electric potential. So the electric potential, we're going to call that capital V with 2 bars. Okay, so this is how I'm going to write potential. So hopefully you guys have been paying attention that when I write volume, that's a single bar on top. Potential will have 2 bars, so we can distinguish which one is which. Velocity has 0 bars to it. So, write that on the side here. So for me, this is volume. This is potential, or electric potential, which we usually just call potential. And this is velocity. So that way you know which V I'm actually talking about. So put that away over here. Unfortunately, my handwriting is fantastic, so it's hard to define which one is which. So that's how I'm going to do that. So good. So let's go back to potential. So here, we're going to call this guy what's known as the electric potential. We're going to denote that by V. Electric potential, by definition, is the electric potential energy per unit charge. So this is what we call electric potential. Now, we know energy has units of joules. Charge, we know, has units of coulombs. So this thing is what we call a joule per coulomb, which is also what's known as a capital V, which is equal to a volt. So this is the units of potential. So a lot of times I'll just skip the electric part, and I'm just going to call this guy potential. So what does this mean? Now, first of all, before we move on, notice that potential then has an ambiguity just like potential energy does. So as I mentioned up here, if I define then here, the top of the stage as my 0 potential energy region, then this thing has a certain amount of potential energy. But if I instead define where Nathaniel's feet are, at the bottom of the floor here, as my 0 potential energy region, this thing now has more potential energy because I defined my 0 differently. Since this thing is defined in terms of this, which has that ambiguity, that means this has that ambiguity as well. So the amount of potential in volts I have for a particular object or for a particular charge at a particular point depends on where I define the 0 to be. Which ultimately means that the potential that this thing has at a particular point is a useless quantity. It's useless. Because for this to make sense, you need to know where I define the 0. If I don't tell you that, then that number makes no sense. Who cares about that number? So if you think about what we did when we talked about conservation of energy, how did we get around that? Well, we got around that by saying what's important is not how much potential it has here, but how much potential changed from this thing going from this location to this location. So when it comes to potential, just like potential energy, what's important to us is not the value of the potential at each point, but the change in potential. So what's going to be important to us is actually the change in potential, which is what's known as voltage or potential difference. So this is actually what's important to us. So potential difference then, or voltage, delta V, which is then equal to the potential at, say, point B, minus the potential at point A, then is equal to the change in potential energy divided by the charge. But since the change in potential energy is related to the work, this is actually also equal to negative the work divided by the charge. So this means then that voltage, or potential difference, is then equal to the change in potential energy per unit charge, which is equal to negative of the work done divided by the charge. So the big thing to get out of here is that the change in potential energy then is equal to the charge times the change in potential. So the change in potential energy, or the electric potential energy, is equal to the charge times the change in potential. So what does this mean? So what this means is if I measure the potential difference between 2 points, then I know the potential difference between the two, which means if I take that and I multiply by the charge, I also then know the potential energy. Once I know the change in potential energy, I can then use conservation of energy. And now I can rewrite conservation of energy in terms of the change in electric potential as opposed to the change in gravitational potential or spring potential or any of these types of things. So all this means is if I was looking at some region and I took my voltmeter, here's my voltmeter, and I put one probe here and I put another probe here, and I measure a potential difference between the two of, I don't know, let's say 5 volts, then that means that my change in potential is equal to 5 volts, which means my change in potential energy then is equal to whatever the charge is times that 5 volts. That's it. Now, we'll talk more about potential, but the reason we use potential, as I talked about in the video for the lab, is that potential, as we're going to see, is actually a scalar quantity. And we know it's a scalar quantity because, again, it's related to potential energy and it's related to work. Both of these are scalar quantities. So the nice thing about potential is that potential is a scalar quantity, which means unlike an electric field or force, it doesn't depend on direction anymore. Which means if I'm trying to determine, say, the potential between 2 points, I don't care that they're like this, or like this, or like this, or like this. The direction doesn't matter. The only thing that matters is the absolute value between the two. So direction doesn't matter. The other thing that we're going to talk about later, and that you've actually already seen in lab, is that it's intimately related to the electric field. So if I know the change of potential, I also know the electric field. So now I know what the electric field looks like as well. So good. So now that we know this, all this says then is we can now use conservation of energy and say that now our change in kinetic energy plus our change in electric potential energy is equal to 0, which means our change in kinetic energy plus the charge times the change in potential is then equal to 0. Okay, so this is electric potential. So again, electric potential is simply the electric potential energy per unit charge. So what it really means is 1 volt then is the amount of energy per unit charge it takes for me to move it across a 1 volt potential. This is what that means. Good, so let's do an example. You guys don't want to see quantum. So this says, in the figure below, we have a charged particle, either an electron or a proton, which we must first determine what it is moving rightward, so it's moving in this direction, between these 2 parallel plates, which are separated by a distance of 2 millimeters. So this distance here is 2 millimeters. And we're told that the left plate here is at minus 70 volts. The right plate is at minus 50 volts. The particle then is slowing from its initial velocity of 90 kilometers per second down to a slower velocity. So initially this thing is moving in this direction with 90 kilometers per second, slowing down as it moves to the right. So first thing we want to know is this an electron or a proton? And then finally we want to know what's the speed of it by the time it reaches the second plate. So these are all the things that we want to know. So good. So let's talk about this. So here's my 2 plates. So we're told this one's at minus 70 volts. This one is at minus 50 volts. We have a charged particle here of some charge Q, where we know Q is going to be equal to E, because it's either a proton or an electron. We just don't know if it's positive or negative. And we know the initial velocity points in this direction. And we know that by the time it reaches here, it has a final velocity V, which was less than the initial velocity. So good. So the first thing we want to know is, what is the charge? Is it a positive charge or a negative charge? So meaning, is it an electron or a proton? So first things first is, notice that I gave you minus 70 and minus 50, but again, what we care about is the difference between the two, not the actual values of each one. Which means that if this is negative 70 and this is negative 50, what's the difference between the two? What's the difference between the two? So if one's at negative 70, one's at negative 50, what's the difference? Or positive 20, right? There are 20 difference from each other. Which means that instead of calling this one negative 70 and this one 50, negative 50, I can easily call this one 0 and this one 20. Doesn't change anything, doesn't change the difference, right? So we're gonna go ahead and do that. So let's say instead of calling it this and this, I'm gonna call this one 0 and this one 20. Now, what this tells me then is that the potential here is greater than the potential here, which means the potential energy here is greater than the potential energy here. So let's go back to what we talked about in the beginning. The higher potential energy than one means it also has a high potential, which goes with then the positive plate. The low potential energy one means it then has a low potential, which means that one corresponds then to the negative plate. So from here, if this is high potential energy, this thing also then has high potential. This one is low potential energy, which means it also has low potential. Which means then that the positive plate equals then the high potential, and the negative plate then equals the low potential. Okay with this? So let's go back to our figure here. What that means then is that this is the high potential, which means the high potential then corresponds to the positive plate. So this side then must be the positively charged plate. This one here, which we arbitrarily set to 0, then has a lower potential, which means this is the low potential side, which means this one then has to have negative charges. So the low potential corresponds to the negative plate, the high potential then corresponds to the positive plate. So what does that mean? So that means then that the electric field points from the positive plate to the negative plate, which means my electric field then points in the negative x direction in this case. So what's happening here? So we know that the velocity here is greater than the velocity here, which means that as it moves from this location to this location, it slows down. Which means if it slows down, what's the direction of the acceleration? Good, in the negative x direction. Which means this thing has to have an acceleration pointing this way, which means the force also has to be in the same direction. So the force on this guy is pointing in the same direction as the electric field. If the force is in the same direction as the electric field, does that make it a positive charge or a negative charge? So if the force is in the same direction as the electric field, does that mean that guy's positive or negative? Remember that force is equal to charge times the electric field. So if this guy points in the same direction as this guy, is this guy positive or negative? It's positive. So this thing has to have a positive charge. The other way I can think about it is this particle is going from a low potential to a high potential and it's slowing down, which means it's doing that. As it goes from a low potential to a high potential, it slows down, which means, again, it has to have a positive charge. So if this thing has to have a positive charge, then this thing must be, which one has a positive charge, proton or electron? Proton. This has to be a proton. Good. So good. So from here, part B then wants to know, okay, how fast is this thing going at point B, right? By the time it reaches the other plate. So now we know that we can say the kinetic energy change plus the potential energy change, in this case is the electric potential, must be equal to 0 because there are no non-conservative forces in this statement. So one thing that's pretty much always going to be true in this class, at least this semester, is the work done by the non-conservative force will pretty much always be 0. Which means that there's no air resistance here. There's nothing taking energy away from our system. So good. So this is going to be equal to the change in kinetic energy plus the charge, which is the fundamental charge because it's the proton, times then my change in potential must be then equal to 0. This is then 1/2 m times v final squared minus 1/2 mv initial squared plus E times the change in potential must then be equal to 0. Or in this case, we know the change in potential is simply equal to 20. This is 20 volts. Let's now solve this for the final velocity. So this then tells me that the final velocity is equal to the square root of twice the mass divided by 2 divided by the mass times then, so this is going to be, if I can do that math in my head, 1/2 mv initial squared minus E delta V. So this is then my final velocity. Okay, so here m is the mass of the proton. So the mass of the proton is 1.67 times 10 to the minus 27 kilograms. E is equal to 1.602 times 10 to the minus 19 coulombs. Delta V is equal to a positive 20 volts. Looking at our numbers, what we should find in this case then is that the velocity works out to be 65.29 kilometers per second. So this is my velocity. Now from here we can see that the velocity indeed has to be less, and the reason for that is because of this negative sign. And the negative sign is going to make sure that this thing is less. So the left-hand side will be less than the right-hand side. So it's moving slower as it should. Okay? What's up with it?
Are the masses, the value of E and the constants that you given?
Of course. Yes. 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 Yeah. So on the exam, yeah, on the first page, I'll give you the mass of the electron, mass of the proton, fundamental charge, what K is, all that good stuff. Yeah. Yeah. So don't bother writing any of that stuff. Let's do another example. So the next one says, it eventually opens. There we go. Suppose we have a cathode ray tube. That's what I showed you in the beginning. That an electron inside of the cathode ray tube is accelerated from rest through a potential difference of 5,000 volts. What is the change in electric potential energy of the electron? And then what is the speed that the electron has after it exits then the cathode ray tube? So basically what's happening here is I have a cathode with an anode, which means there's an electric field across here. So this is my positive plate, negative plate. The electron then is going to be accelerated through here. So it starts here. It's accelerated through this region, comes out through this hole, which then it moves with constant velocity. Mm-hmm. Now what this is saying then is that the potential difference from this point to this point is 5,000 volts. So first thing it wants to know is what is the change in potential energy, and then what is the velocity at which it comes out with. So part A, first things first is we know the change in potential energy is equal to the charge, which is that of an electron. Actually negative, let's do it this way. Charge times the change in potential, which is then equal to minus E times delta V. So this is equal to minus 1.602 times 10 to the minus 19 times then the potential difference, which is 5,000 volts. Plugging our numbers, we find out this is about negative 8 times 10 to the minus 16 joules. So this is the change in potential energy. Part B then wants to know, well, how fast is this guy coming out if it starts from rest? So again, we're going to use conservation of energy, which says our change in kinetic energy plus our change in potential energy, electric, is then equal to 0. So this is then 1/2 mv final squared minus 0, because we're going to assume the initial potential, or sorry, initial kinetic energy is 0, plus then my change in electric potential energy is equal to 0, which means the final velocity then is equal to the square root of negative 2 times my change in electric potential energy divided by the mass. Now, don't be worried about this negative sign, because usually if I had a negative sign under a square root, that gives me imaginary. But this negative sign will kill off this negative sign, which means this thing is going to become positive at the end. Okay? So good. Plugging my numbers, what I find in this case then is this works out to be about 4.2 times 10 to the 7th meters per second. Now, one thing I'll point out now is that this expression here, this expression is actually true regardless of the fact if the electric field is constant or not. So it turns out that even if the electric field was non-constant, this expression is true. That the change of potential energy is simply equal to Q times the change of potential. So this is actually a true statement, regardless of the type of electric field that I have. So good. So basically all we're doing here is we're swapping out one potential energy for another potential energy, and then we're doing conservation of energy. Okay. So the next question then is, well, how then is the potential related to the electric field? So we want to know, how are these guys actually related to each other? So first things first, let's drop the fact that the electric field has to be constant, and let's talk about any type of electric field. So if we go back to work, what we know is that work is equal to the integral from A to B of the force dotted by the differential length. So what does that mean? So that means is, if this is my x, y, z three-dimensional coordinate system, and this is my initial vector A at my initial starting point, this is my final vector B at my final resting point, and this is the path I might carry these over. So DL then is the differential line segment, which then points tangential to the path at this particular point. So this just says that the work going from A to B is integrated along some pre-described path going from this point to the next point. Now, in our case, if we're dealing with an electric field, that simply means that the force is equal to the electric force, which is then equal to the charge times the electric field. So I can then rewrite this as the charge times the integral from A to B of the electric field dotted then by the differential length. So this is then the work done by the electric field. But simultaneously, we know the work done by the electric field is equal to negative the change of potential energy, or the electric potential energy, which is also equal to negative the charge times the electric potential. So if I put all these things together, what we finally find then is that the change in electric potential, also known as the voltage, is then equal to minus the integral from A to B of the electric field dotted by the differential length. So what does this mean? So this means that what? If I had a space, so here's my space, and I know what the electric field looks like in this space, so here's my electric field, then I can find the potential energy between 2 points, let's say this point and this point, so let's say this is point A and this is point B, by integrating along some pre-described path that connects these two guys together. So this is my DL. So that says then that what? If I know what the electric field looks like, I can determine the potential difference between these 2 points by simply integrating along this electric field. So now I can determine the potential difference between these 2 points. This is what this tells me. So if I know the electric field, I can then find the potential difference by simply integrating. What this also tells me that if I took a derivative of both sides, so if I took a derivative of the right-hand side with respect to position, what that's going to do is it's going to kill off the integral, and then the left-hand side is then simply going to be a derivative. So if I do the other way, what this tells me then is that the gradient of the potential with a negative sign is then equal to the electric field. Have you guys seen this before? I think we talked about it a little bit in 205. If not, you'll see it in Calc 3. This is what's known as nabla, also known as the gradient operator. So let's talk about the gradient operator. So nabla, or the gradient operator, by definition, is equal to the partial derivative with respect to x in the I-hat direction, plus the partial derivative with respect to y in the j-hat direction, plus the partial derivative with respect to z in the k-hat direction. This is what's known as the gradient operator. So what does this do? So first of all, what this thing does is the gradient operator acts onto a scalar quantity to turn it into a vector. So first of all, this is a scalar acting on it with a gradient, turns this thing into a vector, which then gives me the electric field. What else does this tell me? This thing tells me the slope of a line, right? So remember that a derivative tells me nothing more than the slope of a line at a particular point. This is what a derivative means. So remember, if I plotted some function, f versus position, and this thing looks, say, something like this, then the derivative at this point is simply equal to df dx, which is equal to the slope of the tangent line at this particular location. This thing then is telling me the same thing. This is the slope of the tangent line in 3 different dimensions. So this is 3-dimensional. Now, what's a partial derivative? What a partial derivative means is, if you haven't used partial derivatives before, all it simply means is I'm looking at how my function changes in a direction while holding the other 2 directions constant. Okay? So that means if this is my x direction, and let's say this is y and this is z, let's write that backwards. Let's call that x, y, and z. So it's a right-handed coordinate system. If I move in the y direction, I'm seeing how my function changes in the y while holding x and z constant. I'm not moving in the x or y or z directions. If I see how it moves in the x direction, I'm then holding y and z constant, move this direction in the y direction, hold x and z constant, move upward, and then holding x and y constant. So partial derivative sounds fancy, but it's basically a derivative which just says hold everything else that's not that variable constant. That's a partial derivative. Now it turns out a little bit further that the magnitude of this thing tells me the direction of steepest descent, or actually steepest ascent. So the magnitude of a gradient tells me the direction at which my function is changing the greatest. That's what this thing tells me, right? So what does this one tell me? So this one tells me that if I know the electric field anywhere within the space, I can then find the potential difference between 2 points by simply integrating over the electric field. This one tells me that if I know the potential, I can then determine the electric field anywhere in the space by taking the gradient of the potential. Furthermore, the negative sign here tells me the direction of the electric field points from high potential to low potential, which is something we already knew because we know that the high potential is the positive plate, the low potential is the negative plate. We know the electric field points from the positive to the negative. Okay with this? So let's do some examples of this. How this guy works. So this one says, determine the potential at a distance r from the center of a charged conducting sphere of radius r with a total charge of q when the r distance is greater than the radius, when it's equal to the radius, and then when it's less than the radius. So let's talk about this guy. So here is my conducting sphere, which has a radius of r, which then has what? A total charge of q. It then wants us to find what then is the potential difference at this point, where this is the radius r, so this is part A. Part B is when r is equal to here, so this is part B, and then part C is somewhere on the inside, so this thing is then less than capital R. Good. So how does this work? So first of all, typically when we're dealing with something like this, what we know is, based off what we did with Gauss's law, we know automatically that the electric field on the outside is equal to what? KQ over R squared in the R hat direction. This comes from Gauss's law. This is what we did over this past week. Now here, again, we're looking for the change of potential. Now something like this, we're looking for the point where the potential is going to go to 0 based on the fact that the electric field is going to go to 0. Now for this guy, the place that the electric field is going to go to 0 is when the radius goes to infinity, which means the electric field goes to 0, which is also the place that the potential is going to go to 0. So what we're going to say is we're going to start this thing off at somewhere out here at spatial infinity, so that here r is then equal to infinity, which means the potential at this point is going to be equal to 0. Okay. Then we're going to integrate along the path that connects this point to this point. So I'm going to connect along a path that's going to connect this point to this point. So this is going to be my direction of dl. So dl is going to point along this particular direction. So this means then that the change of potential, which is then equal to what? The potential at point r minus the potential at spatial infinity, because that's where I'm starting, is then equal to minus the integral from the initial position, which is spatial infinity, to the final position, which is r, of the electric field dotted by the differential length. Okay? Now, from the electric field, though, what we see is that the electric field only points in the radial direction. dl, if I wrote it out in its full glory in spherical coordinates, that's going to be r, it's going to be dr in the r hat direction, plus, let's see, now I got to remember all this stuff. So basically, there's going to be a portion which depends on the theta direction and a portion which depends on the phi direction. Now, the theta, phi, and r direction are all, by definition, mutually perpendicular to each other. Which means if I took a dot product between the r hat and the r hat, I get 1. If I take a dot product between the r hat and the theta hat, that gives me 0. And if I take a dot product between r hat and phi hat, that also gives me 0. So the point of all this is even though I drew this line kind of coming in this direction, the phi direction and the theta direction are going to drop out because of the dot product, which means that all I care about is integrating along the line in the radial direction. So what I could have drawn actually instead, which would have made more sense, is actually just write dl this way, where dl in this case then is equal to minus dr in the r hat direction. So I'm integrating inward from spatial infinity to that particular location. Okay? So that means this thing is then going to be equal to minus the integral from infinity to r of the electric field, which is kq over r squared, times then minus dr. Okay? So here the two minus signs are going to cancel each other, so it's going to become positive. The kq is a constant, so that comes out. So now I have k times q times the integral of dr over r squared from infinity to r. Okay? Now, what's the integral of 1 over r squared? 1 over r squared is a negative 1 over r. So if I plug all that in, then this thing becomes my change potential is then equal to negative kq over r evaluated from infinity to r. So put this in, this is then simply equal to kq over r. Good. So what this says then is that, going back to my picture, that the potential at this point at A is equal to kq over r. But what does this actually mean? What this means is that the potential at this point, which is kq over r, is the potential relative to spatial infinity, where the potential is equal to 0. Okay. So what this is actually telling me is it's a potential difference between this point and spatial infinity. Make sense? So even though I'm writing this as simply potential, this is really the potential difference between this point, some spatial distance r outside of the conducting sphere, versus that at infinity. So this is actually a potential difference. So it's potential difference between this point here and spatial infinity. This means at this point it has kq over r worth of potential relative to where it's 0 at infinity. Okay? What about part B? So part B then says, what if R is equal to capital R at the radius? Well, here we know that's what? Our potential difference then, or I'm just going to call that the potential, is simply equal to KQ divided by capital R. So I'm just going to evaluate this guy at little r. Little r evaluated at capital R. What about part C? So for part C, we would then have to do the same thing, right? I would have to integrate this thing from infinity all the way down to some point on the interior. But here we have to be careful because now we have two different electric fields, right? I have one electric field which is on the outside, which is this electric field, and then I have a different electric field which is on the inside. Which means the total integral then would have to be split up into two integrals, where I'd have to do one integral from spatial infinity to capital R, and then do another integral from capital R down to little r, using the two different electric fields. But, since this thing is a conductor, what has to be true about the electric field inside of a conductor? It has to be 0. Which means then, that the integral going from here to here plus here to here is simply the same thing as the integral from here to here plus 0, which means it's simply the same thing as the integral from here to here, which is exactly the same answer as part B, which means the potential difference on the inside is that which is on the surface. That's it. We'll talk more about this tomorrow because I think I'm out of time now. So, again, the point is, if I know the electric field, I can find the potential difference. If I know the potential difference, I can find the electric field. So, tomorrow we'll do some, what happens if I know the potential, how do I get the electric field from there? So we'll look at some gradients. Okay? Y'all look like I beat you up today. Yeah, okay. I'm doing my job well. So.